Our next topic is going to be on momentum. And you've heard that word before, usually in terms of like a sports team. If a sports team has a lot of momentum, it means it's very hard to stop them. And that's going to be kind of our definition. Okay, momentum is how hard it is to stop something. Now, that's a little bit like inertia. If you remember Newton's first law, an object in motion will stay in motion at a constant speed unless it's acted upon by an outside force. And the inertia was its resistance to a change in speed. Okay? Due to their inertia, they want to go at a constant speed unless they're acted upon by an outside force. And we said that inertia was equal to the mass. It's harder to change the speed of, say, a bowling ball than it is a ping pong ball. So these two things are related, but they're not the same. So we're going to talk about the inertia and momentum of several different objects. So the first one is a ping pong ball moving at 20 meters per second. Now, it has a very small inertia. It has very low mass. We'll leave right here that it's mass. Okay, and it's easy to change its speed. If I just stick my hand up, I'll stop the ping pong ball, make it bounce back the other way. So it's easy to change its speed. It also has a small momentum. Okay, momentum is how hard it is to stop. It's easy to stop a ping pong ball. Now, a train at 20 meters per second has a huge inertia. It's very hard to change its speed. Okay, if you put the brakes on the train, it takes a long time for the train to slow down and come to a stop. And it has a huge momentum. It's very hard to stop a train going 20 meters per second. Now, a train at rest, again, it has a huge inertia. Okay, it's at rest, it wants to stay at rest. It's hard to get it to move. I couldn't push it and expect it to move anywhere. But it has zero momentum because it's at rest. How hard is it to stop it? It's not hard. It's already stopped. I don't have to do anything. Our last example is a bullet at 500 meters per second. It has a small inertia. Okay, I could take a bullet and pick it up and wave it around. It's easy to change its speed, but it has a pretty good size momentum. So we'll say that it has some momentum. Okay, if this bullet is traveling at 500 meters per second, I don't want to try and stop it. So there's two things that go into momentum. It's mass, okay, and its velocity. So our equation is going to be P equals mv, where P equals momentum. They couldn't use m for momentum because m meant mass. For some reason, they picked P. So our example, what is the momentum of a 0.01 kilogram bullet at 500 meters per second? So P equals mv. The mass is 0.01 kilograms. The velocity is 500 meters per second. If I multiply the numbers together, I get 5. And momentum doesn't have its own unit, so you just get the unit by multiplying the kilograms times meters per second, which gives us kilogram meters per second. Now, the reason momentum is important is because it's conserved. And what that means is that the total momentum of a system is constant. What it's going to mean is that in the problems we do, we're going to set the total momentum at one time equal to the total momentum at another time. Usually before and after an event. So like before a collision and after a collision. The momentum before is going to equal the total momentum after. Now, for our problem solving, I like to sketch it. Find each momentum both before and after the collision, whatever the event happens to be. Find P total before the event and P total after. And then our last step is going to be to solve the problem by doing P total equals P total. Now, you're going to actually probably find these problems pretty easy, and we have some examples on the next page. So our first example, we have a 200 kilogram car traveling at 30 meters per second, hits a stationary 300 kilogram car. Then the 300 kilogram car is going to move off at 25, and we want to know the velocity of the 200. So like I said, I like to do a sketch of before and after. Okay, so before the collision, we have a 200 kilogram car moving with a velocity of 30. It's a 300 kilogram car that's stationary, has a velocity of 0. Afterward, the 300 kilogram car is going to move to the right, and it has a velocity of 25. And we want to know what's going to happen to the 200 kilogram car. Now, the first step was to sketch it. The second was to find each of the individual momentums by using P equals mv. So for the 200 kilogram car, it's going to be 200 times 30 is 6,000. For this car, it's going to be 0 because I'm multiplying by a velocity of 0. Here it's going to be 200 times whatever v is. And for the 300 after the collision, it's going to be 300 times 25, which is 7,500. Find the total before and the total after. So beforehand, the total is 6,000. After, the total is going to be, I just have to add the two terms together, 200v plus 7,500. Then we finish the problem by setting our totals equal. So p tot equals p tot. So 6,000 equals 200v plus 7,500. If I subtract 7,500 from each side, I get negative 1,500 equals 200v. And v ends up being negative 7.5. The negative means that it's going to be going to the left after the collision. Momentum is a vector. I'll make a note of that over here. So direction matters. So anything going backwards, we're going to make negative. So here's another example. A 400 kilogram car traveling east at 15 collides completely inelastically, we'll discover what that means in a minute, with a 600 kilogram car moving at 8 west. And then what is the velocity of the cars after the collision? This completely inelastically means they stick together. So our before picture is going to be a 400 kilogram car traveling east with a velocity of 15.
Good morning, everybody. This is Mr. Giannotti. Pardon the
And the second car, with a mass of 600, is moving west with a velocity of 8. Our after picture, they're stuck together. So we can treat them as one big object with a mass of 1,000. Just add the two masses together. And I want to know what the velocity is here. So P equals mv. We'll use that for each term, for each part. So we're going to get 400 times 15, which is 6,000 for this one. Here, P equals 600. But remember, I said these are vectors. So this velocity going to the left, I'm going to make negative. So times negative 8. That's going to give me negative 4,800 for the momentum of that car. Then, these two together, it's going to be 1,000 times v. Now I'm going to take this over here. We're going to do p total equals p total. So 6,000 plus negative 4,800 equals 1,000 v. This gives me 1,200 is 1,000 v. So v is 1.2 meters per second. Now you could ask yourself, is it going to be moving east or west? Since the velocity ended up positive, it has to be going to the right in our picture, which was east. Now the last problem, there's basically two types of problems, either collisions or explosions. in a collision, two things come together and collide. In an explosion, they're going to fly apart. So it's like a collision in reverse. So here we have a rifle firing a bullet. The bullet's going to take off with a velocity of 500. And if you ever fired a rifle, you know the rifle comes back towards you. Okay, so we have to draw a before and after picture for this. Now the before picture, before it's fired, they're both at rest. So if they're both at rest, the momentum is going to be 0. The after picture, we have the rifle, which has a mass of 2, and the bullet, which has a mass of 0.05 and a velocity of 500. And we're trying to find the velocity of the gun. So P equals mv. So for this one, we get 2v. For the bullet, it's going to be 0.05 times 500, which is 25. And then I can set P total equal to P total. Okay, beforehand it's 0. Afterwards, it's 2v plus 25. Subtract 25 from both sides. Negative 25 is 2v. And then my answer is that the velocity is going to be negative 12.5 meters per second. So the rifle would come back at you with a velocity of 12.5. Now, some notes. An elastic collision means that the objects bounce apart. With no sticking at all, and kinetic energy is conserved. We haven't talked about kinetic energy yet, but you can calculate it also. This is actually like billiard balls. They bounce apart without hardly touching or without hardly sticking together at all. So they're going to be almost an elastic collision. It's actually impossible to have a collision be perfectly elastic. Inelastic means that there is some sticking. Ke is not conserved. Okay? Momentum is conserved, so we can use momentum like we've been doing, but kinetic energy is not conserved. This would be like when you, say, kick a football. If you see a real slow-motion picture of a foot hitting a football, the football actually deforms. The foot actually goes kind of into the football for a moment, and then they come apart. And when they're stuck together like that, you lose some kinetic energy. Completely inelastic means that they stay stuck together. Okay, some people have the misconception that inelastic means sticks together. That's what completely inelastic means. Inelastic, in general, just means kinetic energy is not conserved.